All right, let's get started. So I wanted to start with a quick recap of what we went through last time and then pause for questions about the overall setup. So we were distinguishing between two particular cases with a particle on a circle and the 1D crystal. And here we said we were doing a path integral to calculate the ground state. We're doing a path integral uh, on a cylinder where our paths went all the way around the cylinder and all possible paths you could imagine on a cylinder with various number of windings. And if we unfold the cylinder, then we get gauge copies of our initial and final states. And gauge fixing the initial state to be one particular state, we said the trajectories look something like this, where we sum over all possible final positions of this, all possible final gauge copies, and the trajectories are various kinds of instantons and anti-instantons sprinkle along the time direction. And for the 1D crystal, we have an intrinsically periodic potential, but each lattice point is physically distinct. And the question we ask is to start from a particular lattice point to a particular final state point, and then we sum over all instantons that go, or instantons and anti-instantons that go between these two specific points. And so our path integral sums over paths, which looks something like this. And the result we got for doing this path integral was sum over instantons and anti-instantons weighted by the theta angle of our theory, which is just an independent sum over n and n bar, which we could just see as two exponentials. And so what we get is which just means that if you look at the large time behavior of this, this is supposed to tell us the vacuum energy of the system, which is the harmonic oscillator vacuum energy, but then the energy has a theta dependence as follows. And in this case, the partition function we got was again very similar looking, where there's again a sum over instantons and anti-instantons. But there's a Kronecker delta that enforces that the number of instantons minus number of anti-instantons be a specific value that depends on which side we are starting from or which side we're ending. For example, if we're starting from 0 and 0, we'd have something like a Kronecker delta of n minus n bar. And this we said we could make into a independent the independent sum by using an integral over phi, and what we get is And so here again, for a given value of phi, we get the energy that looks very similar. But then we have here. We have here, the interpretation is we have for every phi, we have a state um, with a given energy. And so uh, this corresponds to a band of energies labeled by the angle phi, a continuous band of energies. This corresponds to a single ground state, which has dependence on its energy, of the angle theta. And so these were the two systems that we spent some time developing. So any questions about these before we go on? Okay, most people seem either happy or extremely unhappy. So, okay. So what I wanted to finish off still in the context of the quantum mechanics of the theta angle is to show you that the system that we've been studying, the particle in a circle, is uh, uh, actually shows up as the effective system for gauge theories with the theta angle very close to the theta angle in QCD. And so there's a couple of simple systems for which the Hamiltonian is the Hamiltonian of particle in a circle. So all the things we learn and all the intuition we built about the theta angle in this system applies to these systems as well. And we'll see how these simple systems actually are very nice to actually understand details of um, non-abelian 3+1 dimensional gauge theories that eventually we'd be interested in to understand the strong CP problem. So one of the simplest systems we could study is a 1+1 dimensional quantum field theory. So now we're going away from, we're not talking about quantum mechanics anymore, we're talking about quantum field theory. So this is 1+1 space-time dimensions, but we'll show actually the underlying dynamics is that of the quantum mechanics of this particle as well. So 1+1 dimensional Maxwell theory, what would the Lagrangian look like? Perhaps guess that there's a kinetic term, and in 1+1 dimensions, we could also write down this term using the two-dimensional Levi-Civita symbol epsilon mu nu. And so this theta term in 2 dimensions is really the analog of the theta term that we would encounter in 4 dimensions. And you'll sort of want to see that how this system actually is described by a particle on a circle. So the first thing to notice is that we're talking about a 2-dimensional Maxwell theory. Perhaps this is familiar to you that the Maxwell theory describes particles in D dimensions. It has particles with d-2 polarizations. So in 4D Maxwell theory, we have 2 polarizations of the 2 physical polarizations of photon. So that means in d=2, we expect actually 0 physical polarization. There are no transverse directions to actually have electromagnetic waves. So d=0 means that this theory actually has no propagating degrees of freedom. So if we wanted to study propagating degrees of freedom or electromagnetic waves, this would be a really poor example to study, but we're actually after the topological properties and the theta dependence of the theory. And indeed, this theory actually has, these topological sectors, and so this is an example of a topological theory with no local degrees of freedom, but there's the topological degrees of freedom would have would have something interesting to say. Okay, so here's a little bit of a subtle potentially confusing point. I certainly keep getting confused about this every time I think about it. What we're going to do is to put the theory on a circle. So it's a 1 plus 1 dimensional theory. I could choose the spatial dimension to be a circle, and I can put a theory on some S1. Okay. So the key thing that I want to emphasize is that this circle is not going to be the circle of quantum mechanics that we talked about. Okay. So there's going to be two circles in the game here, and the analog of that quantum mechanical circle we'll discover in just a second. But this is what we'll call a spatial circle or a space-time circle. And this circle is going to be distinct from that circle that we're going to be eventually interested in, that will make an appearance very shortly. Okay? The idea is in quantum mechanics, Q that was parameterizing the circle was a quantum operator. In quantum field theory, X and T are no longer quantum operators, they're numbers. The quantum operators are fields. So the circle that we want to really study will appear in field space in this context. Okay? Is that hopefully clear? So keep in mind there's a potential point of confusion that this spatial circle that we're talking about is now no longer the circle in our analogy. Okay, but on this spatial circle, we can define an operator Q which is this loop operator, integration of a mu around this spatial circle S1. Okay, so this is now a quantum operator Q, and it's defined as integrating our gauge field around the circle. Sometimes you draw a circle like this. This should remind you of things we might have seen before, which is a Wilson loop operator, which looks like the exponentiation of this. Of this quantity. Okay. So our operator Q of t is defined as what appears in the exponent of a Wilson loop. Okay. And indeed, this quantity Q of t is directly analogous to the Q of t from our quantum mechanical system. Is there a question? No. So this field operator integrated over a spatial circle now depends only on time. So now it's a quantum mechanical operator in our theory. So now once we actually think about the theory compactify the theory on this circle, we ended up with a 0 plus 1 dimensional theory. The 0 plus 1 dimensional theory is nothing but the quantum mechanics that we started with. So indeed, the 1 plus 1 Maxwell theory is exactly the theory that we have been discussing. So we can write the Lagrangian for Q, or the action for Q, for example. So the action for Q looks like this. This is exactly the action that we wrote down for our particle in a circle. Notice what are the symmetries that we wrote down that we thought about for the particle of a circle. There was a gauge symmetry. Which was Q, it was identified with Q plus 2 pi. In order for the Wilson loop to be gauge invariant, we would certainly want this to be. We certainly see that integral of a shifted by 2 pi is the same as integral of. So the statement of gauge invariance of the Wilson loop translates into this gauge invariance of our Q variable under this gauge transformation. So Another way to say it is that the Wilson loops, or this operator A, our gauge theory, had large gauge transformations under which integral of A was not invariant, but the Wilson loop, which is exponentiation of the integral of A, is invariant. Don't think we would use this very much, but sometimes you would see this written in one form notation. So this thing can be written as just an integral of the one form A, which is this defined as A mu dx mu in this case, over the circle S1. Okay. So indeed, there's a large gauge. There's gauge transform. There's a gauge symmetry in 1+1 Maxwell. There is large gauge transformations in 1+1 Maxwell, which leave the Wilson loops invariant, but not the integral of A on circles, and those large gauge transformations are precisely the large gauge transformation that we've been talking about for particle in a circle. You'll notice that in this case, we actually don't get a potential V of Q. So we also actually have a global symmetry, which we only had for zero potential in our example that we were studying. The global symmetry is in this Lagrangian is just a shift symmetry of Q by something other than 2 pi. So Q goes to Q plus some constant. You could ask, what is the origin of this global symmetry in the context of the gauge in the 1+1 Maxwell theory? So in the 1+1 Maxwell theory, what we would have said is this symmetry follows from this loop integral over A, shifting by a constant by the same constant, or in other words, it's a symmetry of the Wilson loop by some kind of phasing. So there was an extra symmetry that we often don't talk about traditionally in the Maxwell theory, which is a global symmetry. Here it's manifest as the shift symmetry of Q, but it doesn't show up as a simple symmetry in terms of A. This is what is called a one-form symmetry. So this is the statement that the Maxwell theory actually has a one-form symmetry that's associated with not shifting of A by some constant, but it's shifting by A by some one form, or in other words, shifting of a Wilson loop by a constant. Okay. How many people have seen higher form symmetries before? Okay. With very muted hands. I don't know. You can raise the hands high enough that I can see them. Right. So you see that right away in gauge theory we encounter these notions of generalized symmetries. This notion, the idea that not just local operators but extended operators, like in this case, this operator is not a local operator in our field theory. It's an extended line operator defined around the circle, the spatial circle. That line operator has a symmetry, and that symmetry has physical consequences. In the case of the quantum mechanics on a particle, it's a zero potential. It enforces that the potential is zero. So it's a global symmetry of the system. It's a physical symmetry as opposed to this gauge symmetry that is just a redundancy. Okay. Any questions about this so far? Yes. So this in the Maxwell theory or in the Q? So the gauge transformation literally means Q goes to Q plus 2 pi. So it's not a continuous, it's not, so Maxwell theory has what are called small gauge transformations. So that here there would be these ones that you would normally see as gauge transformations. These are small gauge transformations, but Maxwell theory also has large gauge transformations, and which are not continuously connected to the identity. So they're not continuous, but they're discrete gauge transformations. And the discrete gauge transformations uh, look like this. Sorry, I should let me write it up there. Literally the integral version of this. Where you shift this holonomy by not some arbitrary number, which is a global symmetry, but by 2 pi, which you can see that when you exponentiate it, it leaves the Wilson loop invariant. So the Wilson loop has this extra discrete gauge invariance where you change the phase by 2 pi. That is a part of the gauge transformations of the original theory, and it's a large gauge transformation, precisely like when we said q and q plus 2 pi are identified with each other. It's a large gauge transformation. Okay, does that help? Any other questions? So this idea of higher form symmetries appearing in gauge theories is ubiquitous. In fact, 3 plus 1 dimensional Maxwell theory also has this one form symmetry that we just talked about, which is again the scale, in terms of Wilson loops, it's the phasing of Wilson loops by this phase, or it's shift of the integral of A by a constant. Or an equivalent way to say it is to say it's in form notation. It's a shift of A by a one form parameter, a constant one form parameter. But in terms of Wilson lines and loops, that's what it says. So the idea of these higher form symmetries is exactly that there's interesting symmetries, global symmetries of your theory that are also symmetries of line operators or extended operators, which can actually have physical consequences. One final connection that I wanted to notice before, which I wanted to point out before going on, is to say if we, this is a little bit of an aside from what we're saying, but this idea of having describing a theory on a circle, on a spatial circle, giving us one lower dimensional theory. So we had a 1 plus 1 theory, 1 plus 1 Maxwell, and it gave us a system which on a spatial circle, it gave us a system which was a quantum mechanics, so a 0 plus 1 dimensional quantum mechanical theory with some variable q of t that we have been studying for all this time. We could do the same for other dimensionalities. So we could actually do a 5D Maxwell theory, compactified on a spatial S1. So you can imagine you have an extra dimensional 5-dimensional theory, and the 5th dimension is a small extra dimension that is compactified in a circle, and that gives us a 4-dimensional field theory instead of quantum mechanics. And the 4-dimensional field theory you get is the theory of an axion. So the analog of q of t now, q now depends not just on the leftover variable time, but depends on all the leftover variables, x comma t. So it's a scalar field. That scalar field is the axion. So one of the most compelling models that solves the strong CB problem are so-called extra-dimensional axions. And they are a simple generalization, again, of this particle in a circle that we've been studying. Okay? They have the same properties. An axion, we'll see, has the same large gauge transformations, and so on and so forth. So 1 plus 1 dimensional Maxwell is the same as is exactly the same as particle in a circle, and has the same in particular the theta angle and the physics of the theta angle that we described for the particle in a circle is exactly the theta angle for this gauge theory, and so this our toy example is not that toy of an example. There's another interesting system for which the particle in a circle is the appropriate description. Are there any questions about 1 plus 1 Maxwell before we go on? Yes. Oh, no, no, good question. So the Maxwell, so the symmetry, you could have higher form symmetries in general, but the symmetry we are after in this case is the symmetry of the Wilson line. The Wilson line is always a line operator. So this particular symmetry generalizes to a one form symmetry in any number of dimensions. Um, Indeed. So for example, there's always, whenever you have this one form symmetry, there's always a dual. There's usually a dual symmetry that you could talk about. That's so for a p form symmetry, the dual symmetry is d minus p minus 2 form. So there's a p form, and the dual is d minus p minus 2 form. Sorry. So indeed, if we're focusing on, so this is I don't this is I think Ed was going to do dualities but ended up not doing a duality. But if he did a duality, he would find that if you start with the ordinary symmetry, for example, I guess you did duality for the two form, the Kalb-Ramond field, right? So the Kalb-Ramond field is an example of that. So you start with an ordinary symmetry, like a zero form symmetry in 4D. That means you actually have a two form dual symmetry. So if you dualize the theory, you actually get a two form symmetry. So indeed, when you could choose any one form, any number of form. For example, the one form symmetry for Maxwell in any number of dimensions, the dual thing would then be different in different number of dimensions. And so the magnetic operators would actually be different dimensionality. So in general, indeed, there's you can get all dimensionality of operators and that you could get symmetries out of. Good. Any other questions? Good, yeah, so that's a good question. So indeed, most times when we're doing compactification, what we're saying is we're doing something like Kaluza-Klein compactification, where we take a 5D theory. Certainly in this example, let's take 5D Maxwell, we compactify it on a circle. Then what you can do is you can expand the 5D field theory as modes on the circle, so you get a tower of states in the four-dimensional theory, right? So that's the typical statement. For these topological sectors, it turns out, so in this case, for example, the 1 plus 1 Maxwell, this is not, the 1 plus 1 Maxwell theory did not have any local degrees of freedom at all to start with. The only information was this topological information that was in Q of T. So in this particular case, it's not actually a KK reduction. It is actually the content of the theory. So in general, you're right. It's always that we'll compactify, you get a KK tower, and that's a sort of reducing the theory on a circle. But this topological information is actually all of the information in this particular case. It's a little more, that's a little more cool than the usual KK. Other questions before we move on to? Well, so the crucial thing is that it's the theta term is multiplying something that is a total derivative. So in 1D, that's just there's only one derivative. In 4D, we would have theta multiplying f tilde. So it has it's a two derivative term, but it's a total derivative of something. So let me write instead of just saying words. So in this example, we had in the 2D example, our theta term looked like theta f, or if you want to write out components, theta f mu nu epsilon mu nu. So that's a one derivative term. That's all you can write down in 2 dimensions. In 4 dimensions, this looks like theta f mu nu f alpha beta epsilon mu nu alpha beta. So this is again, this is now a 2 derivative term, right? But this is also equal to something like a mu f mu nu f alpha beta epsilon mu nu alpha beta. Okay, so this is still, it's still true that it's a total derivative, and that is the point of not contributing to local degree to local dynamics, but just as a topological sector. This is sometimes called the Chern-Simons current. So this is sometimes called k mu, and in general in any odd dimension this generalizes, and the differential form way of writing it is you can, in any number of dimensions, any number of any even dimensions, you can always write this term, which is the top form in that dimension. Good. Okay, so the next system that we want to compare with is the case of the monopole rotor. So now we're going to actually study 3+1 dimensional theory. So getting even closer to the theories we care about in the standard model. We have a 3+1 dimensional Maxwell theory where our Lagrangian looks like this term that I just wrote down. So now we can actually write down a theta term in 4 dimensions, and we're going to actually see that this is going to have a similar behavior to what things we just talked about. So if we write down, if we think of this theory in 4D Minkowski, in 4D Minkowski space, there are no non-trivial topological configurations. So there are no instantons. And there's no theta dependence there's no theta dependence on the physics. So physics is completely theta independent. We saw in our example with the particle in a circle that the place where theta shows up is weighing different instanton sectors with e to the I n theta, where n is the instanton number. So that generalizes in any dimensions. Theta shows up as in the action for the instantons, but there are no instantons in flat 4D Minkowski space. And so theta, for the Maxwell theory theta, in flat space will have no physical implications. So the place where the theta angle does actually show up is in non-trivial topological settings. And the non-trivial topology could arise in I guess, in many different ways, one or two distinct ways. For example, it could just be that we're talking about this theory and we're putting the theory on some torus. We can put the theory, we can study this Lagrangian, this quantum field theory, and we could put it on a torus. So this theory has theory now has non-trivial topology, and certainly on a torus you would have non-zero instanton numbers, and the theta sectors would be the theta sectors would be the instanton sectors would be weighed by different values of theta. But it's not just it's not just space-time topology that it's not just space-time topology that gives the topology for this for a U1 field. Um, it, even in quantum field theory, even if we were doing quantum field theory in flat 4 dimensions, we can have effective topology for Maxwell field. So a simple example for such a situation where the topology arises just within pure quantum field theory is the example of the 2 Polyakov monopole. So either your topology can come from space-time itself, but it could also arise from non-trivial gauge field configurations such as the 2 Polyakov monopole. How many people have seen the 2 Polyakov monopole before? Proper show of hands rather than half hands. Okay, so this is an example. So this is a very interesting example of a quantum field theory where you start with an SU2 gauge theory. Which breaks down to a U1 gauge theory, the one that we're interested in. And you say by an adjoint scalar field getting a wave. So this is very similar. I don't know, did you cover, you covered 2 Polyakov in, okay. So you did, most of you have seen 2 Polyakov monopoles, you just don't know that you've seen it. You've seen it today or yesterday. So just like Ed was describing in terms of strings or solitons or vortices, these are solitonic objects that exist because of the symmetry breaking pattern. And in particular, it's a magnetic monopole, so it's like a point-like particle in your low energy effective theory. It's a point-like excitation, and so it does what you expect a magnetic monopole to do. It has some amount of magnetic flux coming out of it. So it's like the magnetic field around it looks like this. And the reason that it actually allows us to have non-trivial topology for the gauge field is because when you go into the core of the monopole, you start noticing that you're no longer in the U1 gauge theory. You actually see the full SU2 gauge theory structure of the system. So this is essentially the reason that you actually can get effects of the theta angle in the presence of these magnetic monopoles. Okay, and we'll sort of see how the effects are essentially captured by again the particle in a circle that we've talked about. So it turns out that we could, while it is a fun exercise to go and actually set up a perturbative SU2 gauge theory, do the Higgsing and construct the solutions explicitly, there's actually a nifty thing one could do to capture magnetic monopoles purely in the 3+1 Maxwell theory. We describe the theory in a space with a hole in the middle. So all the physics of the magnetic monopole can be captured by describing boundary conditions. So let's say at the origin, we say that there's a hole in space-time. So it's no longer the space is no longer R3. It's what is usually called R3 minus the origin, or a small region, small region around the origin. And what we can do is we can prescribe boundary conditions at the origin for our fields, and we can prescribe in particular boundary conditions that there's certain n units of magnetic flux coming out of the origin. So if you draw any sphere around the origin, the flux on that sphere, the magnetic flux on that sphere would be n. Okay. So This is equivalent to describing, this is equivalent to the physics of a magnetic monopole in the 2-Polyakov sense. All right. So let's see how what that gives us. So we can write our 4D Maxwell action. Let's see, how do I do this? Right. So this particular boundary condition, what it in particular means is that what we can now study is a Wilson line, like operator, a line operator, starting at the origin and ending at some point in infinity of. So the gauge field would break up into angular. We can decompose the gauge field in spherical harmonics. We would get typically angular modes of the gauge field. We would get radial modes of the gauge field. I don't want to go into all the details of all the other modes. The one mode that I do want to focus on is this mode, which is a Wilson line between the origin and infinity. Okay, so this is the analog of the Wilson line that we drew on a. So in 1+1 Maxwell, we had a circle, spatial circle, and we defined the Wilson. We defined not quite a Wilson line, but an exponent of the Wilson line. We defined this line operator, Q of t, as integral from zero from around the circle, a mu dx mu. In the case of the magnetic monopole, we are saying that the origin is excised. The boundary conditions are such that there's n units of magnetic flux coming out of that region of the origin, and Wilson lines can end on the origin. Okay, so the boundary conditions are n units of magnetic flux plus Wilson lines can end at the origin. In particular, the mode that we want to focus on top of all other modes, is this mode that is the Wilson line from the origin out to infinity at some random point. Okay, this mode, as you might tell by just the variable I've chosen to denote it, is again a particle in a circle. So this mode is what is called a rotor for the magnetic monopole. So the action for just the ignoring the angular modes, the action for the gauge field looks like this. In just the radial and the time component. So in some, I'm skipping a few conceptual points, but the idea is that this magnetic monopole can be thought of as a sort of compactification of the 4D gauge theory on the sphere surrounding the magnetic monopole. So what we get instead of the 4D gauge theory, we get a 2D gauge theory in time and the radial coordinate, and the angular coordinates have been can be kk decomposed as in any compactification. So we're compactifying the 4D theory on a sphere, on an S2, and we're getting an effective 1+1 Maxwell in the time and the radial direction. Okay. And the effective Lagrangian for that is this, except now since we're on a sphere, there's a factor of r squared. So it's not like a compactification on a circle. The radius of the sphere that we're compactifying on changes with r, and so our kinetic term actually has this quote-unquote warp factor in the compactification. Again, the details don't really matter. The idea is we're treating this as a compactification of the angular directions and keeping only the radial and the time direction. So the four-dimensional theory compactified to a two-dimensional theory looks like a 1+1 Maxwell theory with a theta term. The theta term is, let's denote that 4D theta term as theta 4D. So the theta term in this, in the 2D effective theory is given as integral of f over the S2 that we're compactifying on times the theta 4D over 16 pi squared. So if we have a boundary condition that we have n units of flux through any of the S2s, what this gives us is theta 4D times over 4, let's see. So n units of flux through the surface means that integral of f on any on the S2 is 2n pi. And so that when we compactify on an S2, one of the factors of ff tilde give us just an n. You just pick up this flux on the sphere, and so you're left with the other factor of f in the Lagrangian. All right. Let me say it one more time. In differential form notation, what we had was f wedge f. Let's just do ff tilde d for x times theta 4d. This was our 4D theory. When we compactified this, we thought of this as f ff tilde on S2. What shall we call its coordinates? d2x times dr dt. And so I'm not being careful about the indices. I'm just showing you how the compactification gives you the effective theory. So the 4D effective theory gives you a theta term, which is theta 4D times the magnetic flux through the S2 surface times the 2D theta term. So what you get is in the 2 dimensions, you get the term that we were writing before, theta times f. But it descends from the 4D theory. The f tilde, one of the f's, just becomes the magnetic flux to the S2 theory. In particular, if there was no magnetic flux, so we were not describing a magnetic monopole. If there would be no magnetic flux, then the effective theory would have no theta angle. The theta angle depends both on the 4D theta angle as well as the magnetic flux. Okay. So now we have a two-dimensional, 1+1 dimensional Maxwell theory again with a theta angle, and we saw that the 1+1 dimensional Maxwell theory can be mapped onto the theory of the particle in a circle. So our two-dimensional theory, the 1+1 Maxwell theory, again describes a particle in a circle with the quantum degree of freedom here being the Wilson, the line operator from 0 to infinity, and the action is again ignoring some normalization. The action is again theta q dot over 2 pi for a certain choice of flux. I've chosen 2 units of flux for the magnetic monopole. Okay, so what are we doing? What we're saying is that we want to describe 4D Maxwell theory, or 3+1 Maxwell theory, with a theta term. Certainly, if we're describing this on a topologically trivial manifold, there's no effect of the theta term, so we will go nowhere. There is an effect of the theta term on non-trivial manifolds. One interesting effect is the effect of the theta term on magnetic monopoles. The way we describe magnetic monopoles purely within Maxwell theory is by using boundary conditions at the origin, and the boundary conditions we want to use are that Wilson lines can end on the origin, as well as there's some units of magnetic flux coming out of the origin. Those are the relevant boundary condition that models a monopole. Around this background, with these boundary conditions, we can the 4D Maxwell theory actually reduces to a 2D theory, and the 2D theory looks something like that I've written up there, plus angular modes that I've ignored. So the mode that I want to focus on is this particular mode Q of t. That 2D theory, as we discussed for the 1+1 Maxwell theory, is nothing but a particle in a circle theory with the quantum mechanical action very similar to what we've written. The theta term in that action depends on there being a 4D theta term, as well as there being some units of magnetic flux through the monopole. Okay. So that's a lot of formalism, of which I'm skipping some steps. So if there are any, but we're going to get a cool result in just a minute. So that's why I wanted to show you this. So are there any questions? Yes. Um, yes. So indeed. Indeed. There's this description will have a cutoff, and the cutoff would be the size of the magnetic monopole. So the mass of the monopole. The mass of the monopole may also be relevant, but the size of the monopole is the crucial thing that is sort of setting the compactification radius, if you will, for this particular setup. So the excited states of this system will come as the mass of the monopole. And the mass of the monopole, if you looked at the monopole and built it using the Tooth-Polyakov case, so SU2 broken to U1, we would get W bosons from the SU2 breaking. The mass of the W boson sets the size of the monopole. So indeed, if you actually probe the theory at distances shorter than the inverse mass of the inverse size of the monopole, you'd see that there's W bosons, and you'll see the whole SU2 structure of the theory. So this is saying that in the low energy limit, we can model the entire monopole as just boundary conditions at the origin. Thanks. Any question? Yes. So in that case, so typically Wilson line ends on charged particles. If you actually had an SU2 monopole, then the theory is just quantum field theory. There's no boundary conditions you need to specify anymore. But the fact that the SU2 symmetry is restored in the core of the monopole tell you that Wilson lines can end on those W bosons that are going to be excited. So that's sort of the ending Wilson lines on the origin model is modeled by the presence of W bosons in the core of the monopole. Other question? Yeah, sorry. The quantization of magnetic charge. Yeah, so the quantization of magnetic charge, magnetic flux or magnetic charge, depending on how you want to phrase it, is a statement of the nature, the U1 nature of the symmetry. So the statement that on any S2, this is 2n pi. This is just as long as you want to say that there's a U1 gauge theory. So the U1 gauge theory, what does U1 mean? That means that there's some phase rotation by which if you do the phase rotation, you're doing nothing. So in other words, u1 is always e to the I alpha, and doing a phase rotation where alpha equals 2 pi does nothing. And so as long as your theory is a u1 theory, the flux quantization of magnetic flux is through any closed surface is a true fact. Um, yeah, I think I should mention this. I think maybe you asked the question in Ed's presentation about magnetic flux through superconducting strings, and that's a slightly different notion of quantization. There, the quantization is not. It's not. So if you have a superconducting string, then you're thinking about flux through this area. This is not a closed surface necessarily. And so the quantization of flux through the superconducting string is a slightly different concept than this, this is just saying I'm talking about a U1 theory, so the magnetic flux through any closed surface has to be quantized. The quantization of magnetic flux through strings is more of a dynamical statement that depends on the properties of the strings itself. So there's an interesting subtlety for you to go down the rabbit hole of. So where were we? Okay, so we through skipping some calculation and conceptual steps, hopefully I've convinced you that there's an interesting mode in the presence of a magnetic monopole for a U1 gauge theory, which looks like particle on a circle. And the particle on a circle certainly had physical effects from the theta angle. So we want to understand what this theta angle does, and what is its interpretation back in the 3+1 dimensional Maxwell theory. Okay. So the effect of this theta angle in the context of the particle on a circle is that the expectation value of the q dot of q dot itself is not 0, but theta over 2 pi. Right. So this is you can look at it from equations of motion, or we could look at it from the ground state of the oscillator. But the idea is that the physical effect of this theta term is to produce a non-zero expectation value for q dot, the operator q dot. Q dot in our 1+1 Maxwell theory was let's get the normalization right. So including factors of r squared, what this matches onto is that FRT or the electric field weighted by this quantity is equal to theta over 2 pi in this theory, or the electric field is there's a factor of E that is really the electric field really is 1 over E. The classical electric field is really 1 over EFRT because we're not really using canonical normalization for the electric field. Barring that electric field, the factor of 1 over E, you see that this quantity looks like a 1 over r squared electric field sourced by a charge, which is equal to okay. So what we discover is that if you study 1+1 Maxwell, if you study 3+1 Maxwell theory with a theta term in the background of magnetic monopole with certain units of flux, we actually find that the classical solution or the expectation value of the electric field is non-zero. So we also have an electric field, and the electric field seems like it's sourced by something which is of charge theta e over 2 pi. Okay. So there's a physical effect you could go and measure. You can measure the electric field around a magnetic monopole, and you'd measure a non-zero value. So certainly theta has a physical effect. This effect is called the Witten effect. The fact that magnetic monopoles pick up electric charge in the presence of a theta term is called the Witten effect, and that's the uh, it's a famous effect of the theta term even in even in abelian gauge theories. Okay, so the entire physics of the Witten effect resides in again thinking about just the rotor degree of freedom, which we modeled as this which we modeled as this line operator from the origin to infinity, and its expectation value, the dot of that operator, gives us the electric field, and so uh, the entire information about Witten effect is already captured by this part of the 3+1 dimensional Maxwell theory, which is parameterized by particle in a circle again. So this theta dependence that we saw, and we spent some time looking at the subtlety of where the theta dependence comes from, is actually a very good model for where theta dependence shows up everywhere in gauge theory. At the end, at the core of every theta dependent term, there's a particle in a circle somewhere with a theta dependent spectrum. Okay. Yeah, so I haven't given you a full presentation of a magnetic monopole here, but hopefully the steps I've skipped doesn't distract from the final result, that actually the theta dependence that we've seen, say the Witten effect, is nothing but the theta dependence that we saw in the energy spectrum of a particle on a circle. Okay. So that is more or less what I wanted to say about the particle on a circle. And I wanted to move on to the standard model afterwards, so this is a good time to pause for questions about any of the stuff we've talked about so far. Oh, by the way, I should say, someone was asking me yesterday, I am writing down notes that I will make available. Yeah, I just want to make sure. There's probably still full of typos, but I want to make sure they're not full of glaring typos before I make them public. Hopefully, over the course of the week, I'll make bits of them public, and I'm still working on them. Last chance for particle in a circle before we dive into the standard model. Okay, so we're going to shift gears now, and we're going to talk about the theta term in the standard model. And it's focusing more on its phenomenological role. And really, this is done in two parts. One is to just think about the standard model at high energies, much above the QCD scale, where it's a perturbative theory, and think about perturbative aspects of the theta term and how it shows up. And when we hit the QCD scale, then the QCD description of the theory becomes no longer useful. It's strongly coupled, and so we have to move on to an effective description, which is the Carré-Lagrangian. And so the first part, which we'll probably end on today, is to just think about the standard model as a perturbative in the perturbative QCD regime, and think about how the theta term appears there. And the next time we'll talk about Carré-Lagrangian, where we see how the theta dependence in QCD can be matched onto theta dependence in the Carré-Lagrangian. Okay. So we write down the standard model in some condensed notation. So here's the standard model with some number of indices suppressed. I've not separated out all the three gauge groups. This is supposed to stand for QCD, SU2, and U1. For each of them, you'll have a theta angle. So there'll be in a priori, there'll be three theta angles, one for QCD, one for the hypercharge, and one for SU2 weak. These are all the fermions in the standard model with the appropriate covariant derivative depending on their gauge charges. And then there are the Yukawa terms that eventually will give mass to the fermions. So hopefully, almost all of you have seen this before, and the notation is not too compact for you to cause confusions. So one key aspect, perturbatively, that we want to understand, that we want to highlight is something called the chiral anomaly. And describing the anomaly would itself take a lecture or two. So, but I also expect many of you have seen at least the chiral anomaly in various courses. So let's take a simple. So this will be an exercise for you to do, and the notes will have the exercises detailed. And so if I don't give you enough details for what the exercises, the questions are written down more carefully on the notes themselves. So the exercise is the following. Let's look at a simpler version of the standard model, which is QCD with one flavor. So this is QCD. And one flavor means here that one flavor massless. That means here we have two wild fermions, say up and up conjugate. No mass term. We could gauge invariance doesn't prevent us from writing down a mass term for the up quark here, but let's work with a theory that does not have the mass term, and so this is it. Okay. And so this theory seems to have independent phasing symmetries of U and U conjugate. So for example, we could do a rotation. We could do a phase rotation of just U and not U conjugate, and the Lagrangian at least seems invariant under this rotation. So this is what is an example of a chiral transformation. But this transformation, even though it looks like leaves the Lagrangian invariant, is actually anomalous, and so it does not actually leave the partition function invariant, and all the various ways of thinking about anomalies, either using triangle diagrams or using the measure, the variation of the measure under this chiral transformation. So the Fujikawa method, all of these different things, different ways are ways to show that a chiral transformation, an anomalous. So I guess the exercise is to show chiral transformation is anomalous. And this is any quantum field theory textbook would do it, at least in the triangle diagram way. You could also find it using, you can also follow you can also follow discussions which actually do the Fujikawa method of using the path integral and then doing the transformation of the measure. And the upshot is that a chiral rotation in this case is the same as shifting the theta angle by this angle alpha. Okay. So this is an important feature of how theta angle behaves in theories which have chiral fermions. The chiral rotations or anomalous rotations of chiral field of fermion fields shifts the theta angle away. And so clearly, if this is true, the physics of the theta angle would depend on whether there's chiral rotations. So in particular, if we had actually a theory which looks like this, really a theory with a massless up quark, naively what you would say is, I can always do a chiral transformation and get rid of the theta angle in the Lagrangian altogether by doing a chiral rotation by alpha equals theta. And so this is we're going to talk about the massless up quark solution to the strong CP problem in great detail. This is a toy sampler of already how that might play out. When you have fermions, chiral transformations interplay with the theta term, and that is a direct consequence of the chiral anomaly. The transformation leaves the Lagrangian invariant, but the measure not invariant, for example. And so that the effect of that measure shift is to shift the theta angle. Okay. How many people have seen this before? Good. That's a heartening number of people. So hopefully this exercise would not be a huge grungy calculation, but if you've not seen this before, it's worth following at least the conceptual steps of how this how the chiral anomaly plays out, and at least at the perturbative level, a lot of the physics of the theta angle interplays with these anomalous symmetries. Okay. Good. So using so now I'm going to use this as a given, and anomalous chiral rotations can actually shift the theta angle. So in the standard model itself, the baryon number UN baryon is a symmetry under which quarks transform in this particular way. Say and you can see that this is indeed a symmetry of the Lagrangian. This leaves the Lagrangian invariant. All the Yukawa terms involve 1 power of q and 1 power of u conjugate, and everything else is just something like psi dagger psi. So baryon number is a symmetry of the Lagrangian, but it's actually anomalous with SU2 weak. Baryon number, and more precisely B plus L, the baryon plus lepton number symmetry of the standard model, has an anomaly with SU2 weak. And so doing this rotation, we can set theta SU2 weak to 0. So under a baryon number rotation, for example, the SU2 theta angle would shift by that rotation. So we could choose a rotation to just set the theta of SU2 to 0. Okay. So within the standard model itself, the SU2 angle can be rotated away and is not physical. Okay. So here's a quick. Here's a quick quiz. Why or why not could I do the same thing for QCD? Could I find, in principle, an anomalous symmetry which would shift the QCD angle to 0 as well in the same way? I'm trying to phrase it in a way that doesn't give away the answer. So could I repeat the same trick? So this I've just told you there's actually a symmetry in the standard model that makes the theta angle in SU for the electroweak sector unphysical and can be rotated away to 0. What would it take for us to use the same kind of logic uh, to use that for QCD. Yes. Quark masses would need to be 0. Why is that? But the quark masses didn't need to be 0. I did this symmetry. So why is that for? So I'm not saying all of. I'm sure every one of you will say will be correct. I'm just sharpening your. So I agree. Quark masses would have to be 0. But why was that not the case here? We don't have any massless quarks. We don't need any massless quarks to get rid of this SU2 weak angle. So what is the difference in the two cases? There's another hand up here, and then there was. Yes. The weak theory is not a vector theory. Okay. So weak interactions are not vector like. They different. They um, QCD is vector like, and so that's the reason you say. There's another. UN baryon is not explicitly broken. Again, correct. Okay, so let's put them all together. UN chiral is broken. UN baryon is not broken. This is correct. But why couldn't I find some? So this particular symmetry, I agree, would not work because this is just broken by, say, the Yukawa terms. Why couldn't? Why shouldn't I look just harder and try to find some symmetry which is not really broken, but anomalous with QCD that can help me do this? So everything you've said is correct and part of the answer. I just want to put everything together. Anybody else wants to add anything? Good. So we can already decide that there's a theorem that tells us that it would be impossible to do this for QCD without additional structure, and the idea is related to things you said, which is the SU2 weak is a chiral theory, and if SU2 weak is unbroken, then these quarks would stay massless. So you can the only particles. So only let me say how Weinberg says it. Only particles which Weinberg is only particles whose mass breaks a symmetry can contribute to anomalies for that symmetry. Okay, so this is a general statement about anomalies, that if you have some fermions, we need fermions for anomalies. If you have some fermions whose mass term does not violate a symmetry, there's always a polyvillars type regulator that's available to regulate the theory, and you can show that there are no anomalies in that theory. So the fermions, if you want some anomalous symmetry to play this game to cancel the theta angle, such an anomalous symmetry would arise from fermions whose mass would break those symmetries. Okay, so one example would be something like this: an up quark whose mass would break the chiral symmetry. But we don't have massless quarks. If we don't have massless quarks, then we don't have that option. Another option would be that we would see is that we could have a symmetry which is anomalous, but it is spontaneously broken, much like this case of SU2 weak. So the axion example would again be a symmetry that is an anomalous symmetry, and the fermions that contribute to that symmetry indeed get a mass only through spontaneous breaking of that symmetry. And that is how they can contribute to anomalous for the symmetry. So if you followed our logic again and try to look for something like this for the QCD, you would either be led to positing an unbroken symmetry with something like the massless up quark, or positing a spontaneously broken symmetry, which is something like the axion. Okay, so that's the idea of using anomalous symmetries to get rid of the theta angle one way or the other. I'm also aware of the fact that I'm standing between you and lunch. Good. So so the last thing I want to talk about is running and renormalization of theta in the standard model. Oh, I should, before we go on, I should say that, where should I say that? Should I say that now or wait? Let me say it in words now. We'll do that more carefully when we talk about the chiral Lagrangian. That this at least tells you that if you look at the Lagrangian and this anomaly and the existence of this property, that if you do chiral rotation, the theta angle shifts. That I could do chiral rotations of the quark fields in the Lagrangian at the expense of rephasing my Yukawa fields and shift the theta angle. So the theta angle by itself would not be physical. We'll find that actually there's a combination of the Yukawa couplings and the theta angle that is physical. So the actual physical parameter in our theory would be something that is called theta bar, which we wrote in the beginning of the lectures, which is something like theta minus this. The idea being that you can always rephase the Yukawa matrix, or phase in the Yukawa matrix can feed into the theta angle, and the combination that they feed into is precisely this combination, which is anomalous with QCD. So the rotations which change the determinant, which change the determinant of the Yukawa matrices, this combination of Yukawa matrices by a phase are the rotations which are anomalous with QCD, and they change the theta angle. This combination is physical. It's independent of field redefinitions. Okay. So the physical parameter in the standard model is a combination of theta angle and the Yukawa matrices, and we want to understand understand how it runs and it normalizes. I remind you the whole issue with defining the strong CP problem was that there's another phase of the standard model which we've measured to be non-zero. So we know that there's CP violation in the standard model, which can be parameterized in this particular form, for example. It's not a unique form to parameterize this. And so the idea of the strong CP problem was that we already have CP violation in the standard model through the CKM phase, and so we have no right by symmetries to ask for theta bar to be 0. And usually when this happens, when you have some symmetry breaking parameter already in the Lagrangian and you artificially set another parameter with the same symmetry properties to 0, under renormalization group they mix. And so even if you had 0 for a certain parameter, it gets generated by quantum corrections, right? So what we'd like to understand is how bad is it in the standard model or in BSM theories that imagine if we set theta bar to 0 at some scale, certainly symmetry doesn't prevent it from being generated through the delta CKM phase. And so we want to understand how does delta CKM feed into theta bar through renormalization effects. The non-trivial feature that we've been emphasizing about theta is that it's a topological angle, it's a total derivative, it doesn't appear in equations of motion. So it's a little subtle about how to think about renormalization of the theta angle, especially now, one, because it's a topological angle, but also the quantity that we're interested in is theta bar at the end, which is combination of this topological angle as well as the Yukawa matrices, which are just perturbative objects. So there is some there's a little bit of subtlety in thinking about the renormalization of the theta angle, which is what I wanted to point out to you and just give you the state of the art in the standard model without actually going through the detailed calculations. So there's a very nice trick. So there's various ways to think about, to get around this fact that theta is a topological angle and how do we actually see it appear in Feynman diagrams. There's a very nice trick, I think, due to Georgi and Pays by, I don't have the reference handy, but I'll put it in the notes. And the idea is to treat this theta GG tilde coupling, treat the theta angle as a dynamical field. And you'll see that this is something which we will eventually do when we think of the axion solution of the strong CP problem. We'll promote theta to be a dynamical field. But here is just a trick to think of this as some field, theta of x, GG tilde. So now instead of being a topological term, this is just a vertex in our theory. Let's say with, for example, two gluons and this theta field. What putting the next dependence on the theta field does is for us to be able to put momentum through this line in this Feynman diagram. And so this is the momentum dependence of this line is the thing that makes it not topological anymore. It's just a normal perturbative coupling. And so once it's a normal perturbative coupling, we can just treat it as any other perturbation theory diagram that we would, and we could discuss renormalization of this vertex as we would. And at the end of the whole calculation, set theta equals constant, and that will give us the renormalization of theta. Okay. This is not the only way people use to discuss the renormalization of theta, but this is one nifty way to keep in mind if you ever get confused about it being a topological angle. How do I think about renormalization of a topological angle? Think about renormalizing this dummy vertex or renormalizing the axion gluon couplings in the standard model. And right, so now let's try to estimate where would delta CKM at what loop order would it feed back into theta bar? Okay, so at high energies, at let's say way above electroweak scale, the only breaking of flavor symmetries and the only existence of CP violation is through the Yukawa couplings. So a system that in the far UV, the dependence on the Yukawa couplings would arise from something like this. This is sometimes called the big J Jarlskog invariant. Okay, so if we expect the contribution to say theta bar, which is from far UV, something like J, say, times log lambda. These are dimensionless couplings. So the divergence, if there's a divergent diagram that contributes to theta bar, it would have to be a log divergent diagram and proportional to this big J factor. We can count how many powers of the coupling constant are there in this big J factor. This is a diagram which has 12 powers of the couplings. The determinant of a 3 by 3 matrix will be multiplying 3 of these together, and there's 4 couplings in the expression here. So that's 12 couplings, and so this is a 6 loop. You could put pi's if you want, 4 pi squares in the denominator. This is like a 6 loop diagram. It turns out at 6 loop, there's a cancellation because of essentially symmetry between up and down. If you get a J is odd under the exchange of up and down, and so all the diagrams that contribute essentially have the symmetry such that replacing up to down gives you j2 versus minus j, and so the 6-loop diagram actually cancels. And so the first non-trivial contribution you get is, let's say you add a photon on top of the diagram, which distinguishes up and down now. So you explicitly break that isospin symmetry. So actually this gets canceled. The first diagram you get is something like y to the 12th alpha, or y to the 14th, which is a 7-loop diagram. Okay, which is a, wasn't obvious, is a ridiculously high order to go to for a divergent diagram. So so first of all, if you don't start with, if you don't have a theta bar to start with, and you ask at what order would I have to renormalize it by a divergent diagram, it would be a 7-loop order, which is numerically, even if you take the cutoff to be Planck scale, completely irrelevant for theta bars, for anywhere close to the constraints on theta bar. So by itself, this seems not to be, well, we could ask about the philosophy of whether we should, it's not just loops, but if it's a if it's a log divergent diagram, then we should have had a counter term for theta bar already, and so whether or not we should include it. But the fact remains that it's, the RG running of the theta bar in the standard model itself is rather weak. It's a 7-loop order effect. Question? Right, good. So let's think about the kinds of diagrams that will contribute. There's two contributions for any contribution, any renormalization, any loop corrections with theta bar has two kinds of contribution. One you could phrase in terms of just renormalizing the quark mass, and the other you could and the other is directly contributions to theta bar. And so how do the diagrams schematically look like? A contribution that looks like a renormalization of just the quark mass. So remember, we're trying to draw that diagram, theta glu dual, and estimate the correction to that diagram through quantum effects. So a diagram that comes through the renormalization of the quark mass looks something like this. Okay, so this blob could, in general, so if you look at the paper by Ellis and Gaillard, for example, this blob would have like, arbitrary numbers of W bosons and Higgses, and you can do a power counting carefully of how many Higgses and you would actually need to get the y to the 12 dependence. Okay, so the contributions that look like coming from the, in some sense, the argret YUYD part of the calculation looks something like this. But there's also contributions that, for example, Kriplovich calculated, which looks something like this. Okay, in the language of a diagram like this, it would be where the gluons are not attached to the same external quark lines; they're attached to somewhere in the internal quark line. So that cannot be ascribed as a contribution to the mass matrix. This is really just a contribution directly to the GG tilde vertex. So this is, Kriplovich calls this irreducible. It really just means, I think, it's not coming from the quark mass, but directly through theta. Okay, and at the order for the log divergent contribution, they're actually both present, and they both contribute to the same parametric order. But that's not the dominant contribution, loop correction to theta bar. The dominant contribution is actually a finite contribution. Remember our whole argument about why capital J should appear, which y to the 12th was a high energy argument, where the momenta, all the momenta were so everywhere were above the electroweak scale, and so the Yukawa couplings only appeared in the numerator. But when we go below the electroweak scale, then quark propagators have masses, and for low momentum, the masses would be in the denominator, so you could actually get Yukawa couplings in the denominator. So you actually get lower loop order contributions to theta bar but they're finite because they're proportional to quark masses at the end. Okay, so the let's see if I so the dominant diagram is just useful to know because this is the actual dominant diagram that contributes in the standard model to theta bar, sometimes called the Cheburashka diagram, and I'll let you Google why. And the diagram looks something like this. And so these are W boson. This is a Fermi operator. So this is G Fermi here, G Fermi here. We can make the Fermi the W boson propagators explicit if we wanted to. So it's a four loop diagram, and importantly, the two gluons are not attached externally, but they're attached somewhere here. And if we wanted to retain this external line, then we would put the external line somewhere. So it's a diagram that looks like this. These are called Cheburashka diagrams. They go like G squared, G Fermi squared alpha S. So to make up the dimensions, there's the masses of, there's for some massive mass quark to the fourth with some pi squares and so on. And this turns out to be also much smaller than the 10 to the minus 10 number that that is the current experimental limit on theta bar. Sorry, 10 to the minus 19. Okay, so the logarithmically divergent contributions to the theta bar coming from delta CKM are completely numerically irrelevant. The dominant diagram comes from a irreducible type diagram where the gluons are not attached to the same line. The analysis by Gaius and by Ellis and Gayad, for example, showed that this contributions which look like from the quark masses, they estimated to be only at GF squared alpha S cubed. And this is also an estimate. I don't know if there's actually a calculation that that actually calculates this, but there's a contribution already at GF squared alpha S that that shows up, which is not through the quark masses. It's a direct renormalization of the theta term itself. It's a four loop diagram, numerically still rather small. So the fact that it's numerically small gives us a hope that perhaps it's possible that in far UV, theta bar was 0, and certainly the radiative corrections in the standard model itself don't seem to be generating very large quantities of theta bar. So maybe maybe there was a discrete symmetry of some sort, which we'll talk about in a couple of lectures. The discrete symmetries which told us that there's CP conservation in the UV, CP was violated in some particular way that generated delta CKM for us, but didn't generate theta bar. Loop running of standard model couplings generate such a small theta bar that we would be safe with experiments. So that seems like a viable way to go to try and solve the strong CP problem. What we'll see is slightly more detail then when we talk about these problems is that while within the standard model, the running is really slow. Even the finite corrections are at high loop order. As soon as you start writing down BSM operators, you typically generate theta bar. If you have CKM phase, you generate theta bar at 1 loop, 2 loop order. So this sequestering of the theta from delta CKM is true in the standard model, but not true. It's very hard to arrange actually in any BSM models. And so that's the biggest problem. Any solution using discrete symmetries for the strong CP phases that you want to retain this feature of sequestration, but it's actually quite hard, and you have to invent a lot of structure to make sure whatever you did to generate a CKM phase did not bleed into your theta bar phase at a rather small loop order. You can see, for example, there's papers, again, I'll leave a citation in the notes, where people have done this analysis in SMEFT. And so in SMEFT, there's just a ton of operators. There's like 15 operators or something that contribute to theta bar already at dimension 6 level. And so in general, if you have a theory which violates CP, there's the sequestration in a BSM theory is not guaranteed to be present, and so while in the standard model, this gives us some hope that maybe we can have some symmetry solution to the strong CP problem. Okay. Okay, so I'll stop there. Today we'll start with chiral Lagrangian next time, and hopefully get to the end of it next time.